Thank you for watching Knowledge Academy.
Perfect. So just so you know, we don't have really any agenda. I'm just gonna go over vector calculus overview, starting from the vector field, and just gonna talk about general thing, how the vector calculus be evolving throughout this course. We're gonna talk about and repeat stuff that we learned throughout this course, maybe in a more theoretical way. What are the practical application for them? And that's about it. Okay, so vector field, this is where everything is start. And I told you what is a vector field. Vector field is not nothing but is a representation of every different type of scientific phenomena. So a vector field is a graphical representation of different types of scientific phenomena. For example, flow of wind, right? Number one, flow of wind or fluid, right? You know, the winter is coming, if weather is very cold and the temperature of air is dropping. Now the thing is, if you guys notice, air temp when the temperature is dropping, the velocity of the air is making a big difference. So if today is too windy, even the temperature is not really cold, it making a big difference for us to navigate our life every day, because if the wind is cold, velocity really matter, right? Same thing, if the humidity is a lot, it's going to be matter for us. But if it's too windy, you should be fine. But if the windy, if there is not too much windy, but there is a humidity, a lot of the humidity, we are feeling uncomfortable. But the thing is, can we see all these phenomena from our eyes? We cannot. So we need a vector field. So we make a bunch of vectors, say wind is going from east to west, north to south, or whatever angle. That is why every morning when they give you weather forecast, they tell you the direction and velocity of the wind, so you know that which way the wind is gonna blow. Some of the people actually not paying attention, but sometime if the wind is blowing with our door direction, where our door of the home or the window of our home, it making a big difference for our house, how much heat gonna be lose because of the wind. And if there is no window in that direction, let's suppose the wind is changing the direction, we should be saving a lot of money on gas on our bills, because the wind is not blowing on our door or our window, because door and window are the primary location where air can be leak. Okay, another one is electric field. If you guys probably taking physics course, they also telling you positive charge and negative charge attract each other, right? Positive charge and negative charge attract each other, but you cannot see them, so you're making these lines and making these arrows, right? Can you see these phenomena by your eyes? Probably not. That is why you need these vector field. Number third, gravitational field. Okay. Other one is magnetic field. There is a very cool topic or very cool subject that you should know as a student of engineering probably. Just search somewhere um, gravitational. No, not gravitational. Gravitational is obviously everybody know, but magnetic field, the Earth, magnetic field. Right? Earth magnetic field is a shield. Earth have like very strong and very consistent magnetic field, and that's considered as a shield to protect us from very horrible and danger waves coming from sun, actually that field is a shield to protect us from those radiation came from sun. You go and search it. Can you see from your eyes? Probably not, but they are there. That is why we call it northern light and southern light. Sometimes we hear the word, people go to north to just watch the northern lights and southern light. The northern light and southern light are the one which is causing by this magnetic field. Other than that, we talk about that how the magnetic field is representing, right? So if someone gives you this magnetic field, let's suppose 5I comma J, and that is a wind. Let's suppose it's a wind. W is a wind vector. So wind is blowing 5I and just 1J. It means if you make a XY axis, this is your X axis, Y axis, 5I means you can go 1, 2, 3, 4, 5, and then 1J. So this is a vector. This is a vector. I'm representing this W. And what you're gonna do, you're gonna take this W vector and then it's basically start making a bunch of vectors, pretty much like a W. I try to make it look like W. Maybe they are not very close to all of them, but this is called W. So this is a wind magnetic, wind flow field, right? Wind flow field, you can do that. Then we're learning another cool phenomena about conservative vector field, right? And conservative vector field, we just talk about many vector fields are conservative. And conservative vector field means if I want to do something against or in the favor of magnetic field. Let's suppose if I want to go from my house to my work, this is my house, and that is my workplace, my office. I want to go there, but I want to come back, right? Or I definitely cannot go straight line, so I'm going to use a street or whatever roads and come freeways and come back to my work, and I'm going to go back to a different route, different street, different part of the city, and come back to my home. These are the two tracks I follow. I just want to know which way is more difficult or which way is much easier to follow. This side, the top route, or the bottom route to come back. Should I follow different route, or is going to be effort? Is going to be cost me differently in terms of efforts because work is not free. You're putting efforts and money to do work. So this work done is basically if they dependent on the path, then this field is non-conservative. But if they are independent to the path, you go whatever ways, is gonna pretty much you have to do same amount of work. Then you call it conservative field, conservative path. Okay, and then in order to do that, that's the phenomena. And how do you test? We use test for conservative field. And then what we do, we just take the field, like this is my vector f, and they have m, I, n, j. So I take the m and take the partial derivative with respect to y, and take the n, take the partial derivative with respect to x, and just try to test them. If they are equal, it means they are conservative. If they are not equal, it means they are not conservative. So when the field is not conservative, we cannot apply many kind of vector calculus theorem because it's going to give you different values based on the circumstances. Okay. Then we learn two more things. Vector field is really, so bottom line is that you live in a place, right? Vector field have two phenomena. Number one, I'm going to just draw here. So one we call curl and other one called divergence, right? Usually call curl f, and then we usually write divergence f, and both are vector. Both are vector. Now the thing is, sometime that's your house, right? And wind is blowing around your house, north to east, north to west, like small. But if you take this little box around your house, maybe go to 100 feet, 100 feet, 100 feet distance, like little box, it's gonna be look like this. But if you look at the bigger picture, like your whole city, like whole city, wherever you live. Let's suppose you live in Ann Arbor, Michigan, and that's your city and that's your house. You make a vector center on your house or reference axis on your house, and you look in the vector field. So you think the wind is blowing like this, but if you look at the whole city, wind is not blowing like this. Wind actually blowing like they're making those circles. They have some center somewhere else. Maybe their center is not in Ann Arbor. Their center in maybe in Grand Rapids, Michigan, which is all the way on the other side of Michigan, which is west side, right? So you think if you look at this little box you make it, you think your vector field is this direction, but it's not really. If you go to look at the bigger picture, it has some other center. So this phenomena called circulation, right? This is a circulation. It could be vector field, it could be magnetic field, right? And if you have, let's suppose you have a positive charge here, you have a positive charge, you have a negative charge. I'm saying the field is going to here, to here, to here. But if I look at the bigger picture, let's suppose if I'm going very far and then watch this phenomena from here, this is actually making a big, this vector actually making this kind of field. This vector is making another field. So one center here, one center here. So one circulation is going on here, one circulation is going on here. Okay, and this phenomena we call it curl. How do we calculate curl? We take it the curl by taking a cross product of this gradient times f. And what exactly this telling you, this guy is checking how fast field vary with respect to x, y, and z axis. And you usually write like this. Whenever you take the partial derivative, you actually write like this. But really, what does that mean? How fast the field is changing every time you change the x, y, z. If field is very severe like this, let's suppose you make a field vector like this. Yeah, this vector is very less sensitive to x than y. So if you change one unit of x, it goes to 5 unit of y. So it means you have to be careful, because every time you change a little bit x, y direction change drastically, and you have to be careful how you're going to be doing it. Just like you're going on the highways, very high, fast, very high speed. If you move your steering column a little bit, your car actually going very fast to different lane. You don't have to make like a complete turn to go to the second lane. But if you're going low speed inside the city, go 10-15 miles per hour, you have to make a very significant move of your steering column to go to the other lane, because you are less sensitive in terms of changing the direction because of the speed causing that move. And how did you calculate? You take this, and you just take the dot product. I, J, K. Not dot product, cross product. And this is fx, fy, fj. There is another thing we talk about, that how we're gonna do this. When we do this, make sure this guy is gonna come first. This guy comes first. And your normal the direction of this change will be normal to both of them. So if the field is going this way and you calculating the x, right? The field, this is the fx and this is this, the normal of this little change is going to be perpendicular to you, or perpendicular to both, but 90 degree here, 90 degree here. So basically it's towards us, it's towards us. And that's how we calculate the curve of vector field. This curve actually monitor how hard we moving about a point. Like this point could be here, this point could be anywhere, you can go anywhere. You know, it's not usually on the center, you make the center accordingly. Then afterward, we talk about divergence. And divergence is another phenomena, right? And divergence is that it's, you know, like if it's our body, right? This is our body. And this is our body. In our body, you know, one thing in our body which working all the time, like one thing in our body working all the time is probably our brain. And this brain taking a lot of energy from our body, you know. Brain is actually taking a lot of energy our body to process. So let's put it this way: brain is like your cell phone versus your car. Your cell phone versus your car. Your cell phone does not take much energy because it just need to process the information. Your car take a lot of energy because it has to physically move you. You take grab you, putting you sit in your car, your stuff. Car have a lot of weight. It takes a lot of fuel. So if you're burning gas in your car, they produce a lot of energy. It can be good for maybe 2-3 weeks for your phone, but it's not good for probably 20 minutes for your car because car is relatively big. Our mind is always big, it's very small, our mind, and our brain is always processing information. Now it's producing heat, right? And if I want to see how much heat, right now the winter is coming, you see how much heat is coming out of my skull, that is a vector field, and I can make it. Okay, if it's going out, maybe I can call positive, and if it's going in, maybe I can call it negative. Depends on what interest. And if I says, if I'm interested to keep my mind or my head temperature higher, then I'm going to say the inside one is going to be positive and the things are living is going to be negative. That is why you notice one thing. If you go in, you know, if you go on a winter time, if you touch your skull, right? If you touch your skull, usually you feel your arm is feeling a little bit hard. And the reason is that our skull temperature is relatively higher than our body. So when the temperature is higher, when cold air coming, they take the heat very fast. That's why you notice in winter, everybody cover their head and ears. Head is the essential part. As soon as you cover your head, as soon as you try to use like any kind of hat or just try to cover your head with anything, you suddenly feel comfortable. If it's very cold, you suddenly cover your head. What's happened? You suddenly feel very comfortable because it is stopped blowing the energy or heat out of your head, right? And that is why we try to cover our head, because our head temperature is higher than, you know, the rest of our body. So this is the best way to save the heat. But on the vector calculus implication, it means I'm going to be going out or going in. I can use this phenomena to talk about that. And then we use dot product of this gradient and the vector field. I'm not interested the direction in this phenomena. I'm not interested in the direction, I'm interested in magnitude. So all you can do is taking the dot product of this dot fx and plus fy plus fc ijk. You don't need that one. I also have a ijk here. So I cos I is becomes 1, cos 0 is 1, and we multiply the 2, and then we got some vector, right? We got some vector, and then in this vector we need to substitute the, definitely you need to substitute the coordinates. Like I'm gonna say how much energy is going out or in at a have x y z value. You're gonna take this x y z value, and after taking the dot product you substituting these values here, x y z, and it gave you some number, maybe 32. It gave you some number. Usually when you're taking the dot the divergence is going to give you a magnitude. This one does not give you magnitude, it gives you a vector. Not only you can find the magnitude, but it has a direction as well. Here you only have number like 32 units, and you want to know 32 joules are leaving my head every second because of the head temperature is higher and wind is blowing. Okay, that's what we learned in. Then we talk about how do we go in abnormal shape. How do we go in abnormal shape? So what we did, we take another level and we talk about theorem in vector calculus. And I'm going to show you okay. So I just give you pretty much very depth introduction about vector field, and the reason is that after you calculating these divergence, circulation, and conservation of vector field, you are interested to you have two interests. Number one, number two. Number one, how field change along the path, right? And how different shapes can handle the field, right? So I'm interested in two. Number one, I told you vector field is going like this way, or it's making a circulation, like vectors making circulations. Right now, the first interest I have is that the wind is blowing from your college to your home. That's your college, your home, right? Vector field is going from home to college or college to home, and the vector field is going in different direction. Remember, vector cannot be bent. You cannot make a vector like this. Vector should be making, you can break this into pieces. Okay, you make this vector field along this line. You are interested along the path, like how much field going from here to there is changing, how much changing here, how much changing here, how much changing here, or throughout how much is changing between your home to college. And the second thing you're interested, well, if I, how my head, that's your head, and that's your skull, you're interested, your skull shape is like this, how much heat is going to go out of this, right? And look into that. In winter you try to put the head, right? Winter you try to put the head on your skull to make sure heat doesn't go out. In summer you want to keep your head cool by doing something. Yeah, if it's a temperature is really hot, you want to keep your skull cool, so your 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 head does not actually overheat it, because of the brain is always working, right? Brain is always working. You like it, or you intentionally know, or you don't intentionally know, right? You don't have to be taking a calculus course to make your brain is working. It's always working. Maybe some other stuff you try to think and process. and your brain is actually controlling your body. So it's always working, sometime more, sometime less. But two things is that you are interested to know how can I cover my head in the winter and how can I keep my head cool in the summer. Now you're thinking, yeah, you know what? I'm gonna eat my food and I have like a hot potato. How can I try to make this potato cool down faster so I can eat it, right? Another thing is that you have ice cube, right? And then you are interested to know how long it's going to take this ice cube if you dip into the water or a glass of water. This ice cube is going to melt, so heat is going to go into the ice cube. Then you're thinking, you know what? How about if I cut this potato into two, right? If you're taking this potato and if you want to cool down this faster, the best way is that make pieces. So once you take a potato like this shape and you cut into pieces, like this piece is going to look like this, and this piece is going to be look like this side is going to be look like this. So you can see here, this surfaces is the additional surfaces you add. So now this potato actually cool down much faster because they have additional. If you cut it further, it's going to cool down further. And that's how we develop all the theorem called line integral, then Green theorem, then Stokes theorem, then divergence theorem. Since we have a limited time, I'm going to go over with them real quick. So these are the two things I'm interested in. Number one, line or the vector field. Number two, how the vector field is going to make different on the body. Ice cube I gave you, potato example I gave you, our skull I gave you example. Do you think everybody's skull look like same? No, everybody have a different kind of physical appearance, and then their head size is different, and their temperature and then cooling phenomena is different. Now here we have shape, here we have trace. There's the two keywords, shape, trace, right? We're dealing with different shapes, here we're dealing with different trace of vector field. So the first thing we learn in vector calculus is probably line integral. And before than that, we just talk about that fundamental theorem of calculus. When you took calculus 1, calculus 2, or pre-calc, they gave you a bunch of functions, right? They gave you function, and you take the function, and if the limit is given a and b, you substitute after taking the integral, you're taking the substitute the limit of f b minus f a, and done it. And you're done with this fundamental theorem of calculus. But here you never talk about, how do we really try to put the direction. We don't have any direction. You never talk about the function is given 4x cubed plus 3x squared plus 2. Can you take the integral of this? If it's a definite integral, you put the limit. If it's indefinite integral, just don't leave the limit. You just solve this thing directly and give me some answer. But you never talk about the direction. In vector calculus, we do not work like this. All we do is in line integral, what we do, we take this function and then we say in the direction of dr. So line is going this way. Yeah, which way line is going? That's important. And every time I make a little vector, this r dr actually representing this guy, which way I'm going. Wind is blowing which way. Then we learn about this, how we take we parameterize this guy, and then parameterize our function, and then take the differentiate the position vector, and then multiply with my function, and we can solve the line integral. Then he says this is a very tedious method. This is a very tedious method. We need to find a shortcut, and that is a fundamental theorem of line integral. It's a shortcut. But what is a shortcut is, if you want to write the fundamental theorem of line integral number 1, number 2, number 3, and you're going to usually write like this. We take this change and then dr. We take the integral like a dot product, and then what we do, we just substitute different values of different points. So really what I'm doing here, if I want to calculate, I want to go from here to there in line integral, a to b. Rather than I can integrate the whole thing, I can just substitute the value from this point to this point, how much change. Let's suppose the value, the wind is reach out to your home is 14. The wind is start 17 meter per second and 14 meter per second. So that is your college and that is your home. So you want to know how much wind change from college to home. So why do I do all the math to track the path? All I can do is take this 17 and this 14. So I say 14 minus 17. My answer is minus 3. So you say, you know what? This wind is reduced 3 meter per second while it's coming from my college to my home. It's a slowdown, and that is actually fundamental theorem of line integral. Another way you can look into this phenomena is to take the whole track and take this is your home, this is your college. Wind is blowing and you are interested to know how much is changing. So what you do, you make a bunch of points in the middle, right? Every 4 meter, let's suppose every 4 meter, and you change and you check, you find the delta here, then you find the delta, then delta, then delta, then delta. And then what you do, you just write in these values here by using this line integral theorem, the fundamental theorem of line integral. You see, we are just adding these two coordinates. So all I can do, I can take this coordinate, maybe I can call this point number A, this point number B, and this is what exactly I'm adding. Go to B coordinates and A coordinates into the function and finding the change. So let's suppose you go to 2, then 3, then 9, then 11, then 9, then 8, then 7, then 4. So you're gonna see in here, you see the wind is actually getting stronger, middle in somewhere in the middle, 11 meter per second, then again start reducing, and then go to 4. So really the wind is start 14 whatever, and then it's gonna go stronger and then come down. So if you are interested to know how much it changed, only that is the change. But in the middle is getting a peak somewhere, right? If you are interested to know, yeah, pick this point and get the delta. If you are interested to know from this point to this point, yeah, then get the delta by substituting 2 points. And that is actually what you call fundamental theorem of line integral. Okay, this part is done. This part is done. The trace, right? The trace part is done. I'm gonna go to the shape part. When I'm interested in different object in a shape part, I have 3 theorems. One is 2D shape and 3D shape. So I'm gonna go, this is trace, and here is shape. In shape, I have 2D shapes and then 3D shapes. Okay. So I'm gonna do number 4, number 5, number 6. I have 3 theorems to discuss in this course. One is Green theorem. Green theorem is 2D theorem. And what exactly Green theorem is do if you have any shape like this, right? Like let's suppose you have it like a potato, the one you cut it, and this piece. You says, well, I cut this potato into 2 pieces or 2 sections. I just want to know how much heat is going out of this face, like how much this face contribute to cool down this object, and you are only interested to this. So the bottom line is that you are interested to heat coming out or heat going in, right? If it's ice cube, heat going in. If it's a hot potato, heat coming out. So you're interested in direction. So that's why you're making these arrows. So you want to know if things are going into this or coming out of that. And that's the green theorem is telling you by this D and this C. C is a curve or path, you can call it path. And you make the arrows this way, or you can make the arrow other way. Usually, just like X, Y, Z axes, we are using, this is our anti-clockwise direction, is our positive direction for green theorem. If positive means if you draw this one and things are coming out, just like your right hand rule, right? So if you try to curl your finger along these arrows, if you try to curl your finger, your thumb actually showing you, your thumb is gonna come out like this way, and that's your finger. You twist your finger, and this is gonna be telling you the direction of the quantity. If it's a heat, if it's a sound, if it's a wind or whatever, or it's a water, anything, or any magnetic field, electric field, this is telling the direction. How do we write the green theorem? You're supposed to be taking the double integral with respect to domain, but there is a shortcut we learned, which is also called P and Q. P is our x component of the vector, Q is our y component of the vector. You just do this, and this is a shortcut. So usually we solve this in green theorem, and we solve the green theorem. Then we have a Stokes theorem. Right? Stokes theorem is more important is that if you have a potato, right, this is a 2D, but that's not the 2D once this is a two-dimensional, but the rest of the portion, like the red one, is not 2D, it's a surface. And if you're interested to know about how much heat going out of this surface, then you apply Stokes theorem on this red surface, right? And when you're talking about the red surface, the red surface is important too, but where the heat supposed to be coming from or generating into the system, there's a base somewhere, right? So what we do in Stokes theorem, writing again, it's a curl. And the example I gave you, let's suppose that you have a room and window, how much heat coming into this room, it should be equal to the heat passing the window. And that is a window. This is a window of the potato. How much heat is going in, going out of the potato is through this. That's the one is going to be coming out. So heat going in here first, then it's going to be coming out this white color vector. And that's how you write ds. But you don't solve this one. You solve the line integral dr, the right side. Okay. Now you change your mind. You says, you know what? I want to know everything about the whole piece. Right? You're just making a potato like this shape, like you're interested in a whole potato. So number 1 and number 2, you are interested in both. You want to add them too. Number 1 and number 2, you're going to add them. Total heat coming out of this. And that's actually, we call it object. Why do we call different faces? Just call object or body. So if I give you this shape, right? And if I'm asking you, let's suppose this is a cube, ice cube, or maybe this is a charcoal piece. How much heat coming out of here, 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 the back towards you, all the 6 faces, 1, 2, 3, 4, 5, 6. and we call this, the whole surface we call S, and these vector we call N. N1, N2, N3, N4, N5, N6, doesn't matter how many we are. And the way we're writing this thing, we want to calculate, that is a divergence, that is a curve, this is a divergence of F. That's what the divergence we talk about. For who? Remember the divergence we talk about the center. I'm not interested in divergence only. I'm talking about divergence with this volume. D is this guy. And if this guy is going from 1, 0 to 1, 0 to 1, and then 0 to 1. So I'm going to substitute the value here with 0 to 1, 0 to 1, 0 to 1. And that is my dV calculation or volume. And that's actually gave me the total quantity coming out of this shade, you know. And you basically call dV, or you can call this whole surface. This dV is the part, it's a little piece out you're taking out. So really dV is a little portion you're taking out of this cube, but this whole cube you call it E, right? That is the E you use here. You can call E, you can call D, whatever alphabet you can call, is basically nothing but it's just a domain of the system. But anyway, this is pretty much what do we have about a vector calculus overview in terms of how different kind of theory is applying on this. We already complete the.
Thank you for watching Knowledge Academy. Please subscribe my channel.